So I'm happy to introduce Kalle Kytölä, who will be talking about from Ising model in slit-strip to three-point conformal block of fermionic boundary CFT.
Okay, thank you very much. Thanks for the invitation and the opportunity. It's particularly nice to be giving this pair of talks with SC, who just happens to be here in Helsinki at this time. So we're giving this from the same location. I'll be talking about some joint work with Taha Amin, Shinji Koshida, David Radnell, and SC. A specific setup in which we get some aspects of boundary conformal field theory scaling limits for the critical two-dimensional Ising model that I don't think have been achieved for other models, nor for the Ising model in other specific or generic setups. But that said, we're not, don't expect a full proof that the critical Ising model in two-dimensional converges to conformal field theory, but some aspects of that, hopefully, we'll see. So CFT throughout the talks will stand for conformal field theory. They are theories, quantum field theories that live on Riemann surfaces, and the standard idea is to build these from vertices of this sort, so trivalent string-looking pair of bands Riemann surfaces. And if that's the case, then obviously for a boundary conformal field theory that should live on a Riemann surface with boundaries, and maybe those should be built from these vertices and that look like these cartoon pairs of bands. So that's sort of a motivation for maybe looking at the Ising model in this particular geometry. So in this sort of slit strip with three infinite extremities, one going to the upwards direction and two going to the downwards directions, the right leg and the left leg of this slit strip. So this will be the model we'll focus on in this talk. I thought about doing an introduction to the Ising model, since the theme of both of the talks of today is that. And then doing a second introduction to conformal field theory, mainly for the reason that I want to address in the specific case of the Ising model what is known about the scaling limits, conformal invariance results about at the criticality in the scaling limit, and what is not known, what we'd still like to know. So I'd like to emphasize those aspects in order to see what remains for the future. Then I'd like to state the main result, and then I'll have to discuss the ingredients that go into the statement, and hopefully say something about the ideas in the proof. All right, but I think we can get started with the introduction to the model itself. Surely familiar with many of you, but let's at least make sure we agree what we're talking about. So we fix a finite graph G with vertices V and edges E, and one parameter called denoted by beta and interpreted as the inverse temperature. Then the sample space of the probabilistic model is the set of all plus minus one valued functions on the vertices of this finite graph. And an element of this sample space is called a spin configuration. So to every vertex Z of the graph, it assigns a plus or minus one, interpreted as the spin at the vertex Z. And all of the physics is determined by the energy, how it depends on the configuration, and that's with an overall minus sign, the sum over adjacent vertices of the product of the spins at those two vertices. So the energy is lower if the adjacent spins are pointing to the same direction, and it's higher if they're pointing in the opposite directions. So this is the ferromagnetic interaction in the model. And once the energy has been specified, the standard recipe of Boltzmann and Gibbs is to define a probability measure in which the probability of an individual spin configuration is proportional to exponential minus this inverse temperature times the energy. And the normalization constant needed to make this a probability measure is called the partition function. So that is the basic probabilistic model. Of course, we often want to consider these not on finite graphs, but let's say on infinite graphs. The typical case would be the d-dimensional integer lattice. The definition before doesn't make sense as such, but what you can do is you can take a sequence of finite induced subgraphs, which increase and it eventually exhaust the whole infinite lattice, and then you can define the infinite volume Ising as the weak limit of these probability measures on the finite induced subgraphs. And it is standard correlation inequality, which guarantees that the limit, first of all, exists and does not depend on the sequence of subgraphs you used in approximating the infinite graph. So the quintessential feature of the Ising model arises in this infinite volume limit, namely there is a phase transition between a ferromagnetic phase in low temperature and a paramagnetic phase in high temperature. So if the inverse temperature is high enough, so you're in a low temperature phase, then this energetic preference for local alignment takes over and spins at arbitrary locations remain uniformly positively correlated with each other. Whereas if you're in high temperature, so small values of the inverse temperature, the energy gets multiplied with small constant in the exponential, and it's not, the configurations, the typical configurations look disordered. In particular, spins at larger distances decorrelate with distance. Okay, and in between these two regimes, the ferromagnetic low temperature and the paramagnetic high temperature regime, there is a specific point where the qualitative behavior changes from one to the other. And that's called the critical point or critical inverse temperature. I thought, the existence of the phase transition goes back in some form maybe to 1930s by Pales, and the phase transition is there for all dimensions, at least 2. Right. I thought it's helpful for these pair of talks to take this heuristic but very instructive picture from physics about the renormalization group flow. So when you want to understand the large-scale behavior of this model, then one way of doing that is to put your model on a finer mesh lattice and still look at the behavior of it on the original scale, let's say unit scale of order 1. So here is sort of a picture where you have on the horizontal axis the temperature parameter, and on the vertical axis the lattice mesh parameter, and the line on the bottom here is supposed to represent continuum theories, which are believed to be described by quantum field theories. So the lattice mesh has been taken to 0 there already. To understand the large-scale behavior, when physicists think about this renormalization transformation, which can be thought of as making the model live with the same parameters, live on a lattice which, let's say, twice finer lattice mesh, but then looking at the behavior in the original scale, and these arrows there are supposed to represent that transformation. So if there is a well-defined behavior in large scale, then it has to be that iterating this transformation converges to something, and it has to converge to a fixed point if there's any justice in the world. Okay, so one believes that there are basically 3 fixed points of interest. So if you start from any temperature below the critical one, and you apply these renormalization transformation repeatedly, then eventually you see large distance behavior governed by these low temperature fixed points where everybody is uniformly positively correlated. And similarly, if you start from any temperature greater than the critical temperature, the repeated application of this renormalization transformation brings you to the fixed point where everybody is basically decorrelated. And there is only at the critical point you expect to be able to form a scaling limit, which is governed by the critical fixed point. And in fact, that fixed point, or rather the behavior of the renormalization transformation in the vicinity of that, is what determines all of the properties of the phase transition. So let's say the critical exponents of the phase transition. So this is the physics picture. I'll be talking about taking the scaling limits at the critical parameter value. None of the other quantum field theories on this line can be obtained by repeatedly just renormalizing the same model with the same parameters. So in Sanchul's talk, the temperature parameter is actually adjusted as a function of lattice mesh to reach some of these massive field theories, which are not renormalization group fixed points. Okay, but our focus will be on the critical fixed point. And to wrap up this introduction to the Ising model, I should mention that there are very interesting things going on in different dimensions, but I will be focusing on the two-dimensional case. So there's an excellent overview of what is known in different dimensions by Hugo Dumy in the ICM proceedings from last year. I recommend for all of the aspects that I'm skipping about the Ising model. So that maybe takes us to the second part, the introduction to conformal field theory. So this is what is special about the two-dimensional model. So from here on, the dimension will always be 2, and the inverse temperature will always be critical. In this case, there's a conjecture by, well, in physics, maybe more generally, but very prominently phrased in an influential paper by Belavin, Polyakov, and Chamolochikov in the 1980s, that states that the scaling limits of critical models at the continuous phase transition points should be described by conformal field theories. And it is here that some really remarkable mathematical structures appear. It is very surprising that this simple probabilistic model can exhibit all of these intricate mathematical structures. And I will take the point of view that the main one among those structures is vertex operator algebras. So to justify that a little bit, vertex operator algebras are the mathematical axiomatization of the chiral symmetry algebras as envisioned by Belavin, Polyakov, and Chamolochikov in the first place. But they also connect to pretty much all of the different algebraic structures that you might have encountered already. So they certainly contain the Virasoro algebra as, that's contained in the vertex operator algebra. In certain cases, under certain assumptions, modular invariance properties can be proven for vertex operator algebras. In some cases, the category of modules of a vertex operator algebra is known to be equivalent to a category of representations of quantum groups, etc. So I argue that this captures the essential algebraic structures. At least for the purposes of today's talk, I will argue that this captures the most essential algebraic structures. And of course, so these rich algebraic structures often lead to exact solvability of the model. Right. So then what is known mathematically about this conjecture? Well, first of all, we should say a little bit more precisely what do we mean by scaling limit. And the idea is that one should take correlation functions in the statistical physics model, and then they hopefully, with the proper renormalization, converge to correlation functions of the conformal field theory. So there are celebrated results of that flavor which are known. I'll sort of sketch without providing full details, especially about the boundary conditions, etc. I'll sketch some of those celebrated results here. So if you take a simply connected domain in the complex plane and fix a conformal map of that domain to a reference domain, let's say the upper half plane, and as your graphs, you use square grid lattice approximations of the domain with small mesh sizes. then the following scaling limit results for the critical Ising model can be obtained. So a result of Chalka-Kongler and Izurov states that the following spin correlations converge. So you fix a finite number k of locations in your domain, and you look at the spins at the vertices nearest to those locations. You take the product of that and the expected value of that. So that's a spin correlation in the lattice model. And now if you renormalize by a suitable power of the lattice mesh, then the limit as the mesh goes to 0 exists and is sort of manifestly conformally is given by a manifestly conformally covariant expression. So it involves a conformal field theory correlation function, whatever that means, in the upper half plane, but evaluated only at points which are the conformal images of the locations where you inserted the spins. So this manifestly conformally invariant object. And then there's a conformal covariance factor, which involves the derivatives of your conformal map to suitable powers, evaluated at the same points. Okay, so these types of results are known. A similar result about energy correlations is known. So the energy was the product of two adjacent spins. You need to shift it by subtracting its typical value in the infinite volume. Then expected products of such objects with the proper renormalization converge similarly to conformally covariant objects. So this was enabled by developments in discrete complex analysis in the past 15 years or even a bit more, and gives really concrete information about conformal invariance in the scaling limit of the critical Ising model. But is it a conformal field theory result for the scaling limit result? Does it say that the scaling limit is a conformal field theory? And I would argue that it does not. So it certainly doesn't in any apparent way feature these algebraic structures that were in the prediction, in the conjecture. And in some sense, it cannot see those algebraic structures because, for instance, the vertex operator algebra is supposed to be acting on the space of all of the local fields of the conformal field theory, whereas these are results about correlation functions of primary fields only. So it is sort of impossible that this would capture the algebraic structure in a transparent way, at least, in a very obvious way, at least. So that is the aspect that I hope that our main result for today will sort of add to the picture of what we have from these scaling limit results. So I should say, what is the specific algebraic structure? What is the vertex operator algebra? So first of all, vertex operator algebras are axiomatizations of conformal field theory in the following sense, roughly. So conformal field theories are roughly just a vertex operator algebra together with a category of its modules. So the vertex operator algebra is the chiral symmetry algebra, and the category of modules is sort of the spectrum of the theory. This should be, of course, supplemented with something that you compare with correlation functions, and that something is the conformal blocks of the vertex operator algebra on the Riemann surface where you make the theory live. Okay, but this is in principle determined by the VOA and the category of its modules. Specifically for the Ising model, the physics literature states that the scaling limit of the critical two-dimensional Ising model should be a free fermion conformal field theory. So do we know then what should be the vertex operator algebra corresponding to that? Well, yes, that's a very standard object in the VOA literature. So that is what is known as the free fermion supervertex operator algebra. Super just means that there are both fermions and bosons, so some Z2 grading in the vector spaces. Otherwise, I will not bother too much making a distinction between vertex operator algebras or their super counterparts. All right, but what is a vertex operator algebra? It is first and foremost a vector space, and in this case, the concrete vector space is the Fock representation of an infinite dimensional Clifford algebra. So here I take the convention that the Clifford generators are fk's indexed by a half integer k, and the relation, they are subject to certain anti-commutation relations. So they anti-commute unless the indices add up to 0, in which case the anti-commutator is the unit in the algebra. And that type of an algebra has a standard Fock representation which has a basis of this form. So then this vector space is equipped with the algebraic structure. And the algebraic structure in this case is a vertex operator map. So that is a certain map from the vector space itself to formal series. So formal power series in both positive and negative powers with coefficients in the space of linear maps of the same vector space to itself. For the particular case of the fermion super VOA, the entire vertex operator algebra is actually reconstructed from what is the vertex operator of this particular basis vector, which you obtain by applying the smallest negative generator to the vacuum of the Fock space. And that's simply the formal series where the coefficients are these Clifford generators. Interpreted, of course, as linear maps of the representation of Clifford algebra. If you took more complicated vectors, let's say the one where you apply these two Clifford generators on the vacuum, and then maybe with the appropriate scalar multiple, you obtain a formal series whose coefficients are then the Virasoro generators, and this VOA becomes a representation of the Virasoro algebra with central charge 1/2. And let me once more emphasize that this VOA, this vertex operator map, is really the algebraic structure. And one way to see why that's the case, if we look at the specific power of this power series expansion, then the vertex operator map eats a vector and then outputs a linear map. And that linear map eats another vector and then spits out whatever comes out of the map. So this is a gadget that eats two vectors and spits out a third. So it's kind of a product in an algebra. But now for every power series coefficient, you have a different product. So this is kind of like an algebra equipped with a countable number of products. There are some axioms governing, there are some axioms for vertex operator algebras. I will not list them in this talk. So having, for our purposes, this level hopefully suffices. So I should make one last disclaimer before moving on to the main result. So when I said that conformal field theories are vertex operator algebras together with their category of modules, I was not thinking of bulk conformal field theories, which really should have two chiral algebras, and the full symmetry algebra should actually have two copies of a vertex operator algebra. But what I said does make sense for boundary conformal field theories, where there is sort of just one chirality. The two chiralities in the bulk CFT are holomorphic and anti-holomorphic. Boundary conformal field theory does not have either one of the two separately, but it has sort of the two put together in a particular way so that they algebraically are just one vertex operator algebra. But you should not think that all of the fields in a boundary conformal field theory are holomorphic or that all of them are anti-holomorphic. You need to put the two together in the right way. With that, I think we're sort of ready to at least look at the statement of the main result. So recall that that concerns the Ising model in the slit-strip geometry, and specifically sort of boundary correlation functions at these three infinite extremities of the slit strip. I will make the statement. Oh, by the way, I will abbreviate these three extremities, T for top, L for the left leg, and R for the right leg. So I will make the statement But clearly some things need to be defined more precisely before this makes sense, but let's nevertheless see what the main statement is. I claim that for the critical Ising model in this slit strip with locally monochromatic boundary conditions, the scaling limits of general boundary fields, correlation functions of general boundary fields at these three locations form a chiral 3-point conformal block for the vertex operator algebra that we just discussed on the double of this slit strip with respect to the natural local coordinates that you'd like to use in this geometry. Clearly, some aspects of this require some further elaboration, but let me start by nevertheless making remarks how this fits into the picture that has emerged so far. So the main aspect is that we allow for really general fields, not just primary fields, but this space of fields that we consider includes descendants. And in this way, we have some hope of seeing the entire algebraic structure. At the same point, I should admit that we only do 3-point boundary correlation functions, not general endpoints. So we're clearly not achieving the full level of generality that one might hope for. Maybe even more importantly, unlike Chalka-Kongler and Izurov and the other related results that I mentioned, we are not able to do these types of scaling limits in general simply connected domains, and in particular, the apparent conformal invariance, we can't say that the result is manifestly conformally invariant by saying we compare the limit in one domain to a limit in another domain and relate them by conformal map. We're simply able to do these only in one domain. Nevertheless, the result does contain so it does have the 3-point conformal block in it. And for instance, all of the vertex operator algebra structure constants are encoded in that 3-point conformal block. So in that sense, it captures the full algebraic structure of the conformal field theory that we conjectured to describe the scaling limit. All right, so what remains in this is to start addressing the specific definitions that go into this statement. For instance, what do we mean by the model exactly with the boundary conditions? What do we mean by the correlations of boundary fields? What is conformal block for the vertex operator algebra? And what are these choices of local coordinates? So let's start from the model. The idea is very simple. We do the Ising model literally as before, except that now we condition. So we enforce boundary conditions by conditioning on the spins on these vertical boundary components to be constant. And I mean constant only within a given boundary component. It can be a different constant on the three different vertical boundary components. And I always take the inverse temperature to be the critical one for the square grid. Of course, the Ising model is defined on graphs. So here is the appropriate square grid approximation of the slit strip geometry with the three vertical boundary components sort of emphasized. So that's where we do the conditioning. This is an infinite graph. It would not be difficult to define the Ising model on this infinite graph, but if one were to do that by, again, the same thing, take finite subgraphs and the weak limit from them, but something is lost if you take that limit directly, namely that infinite volume measure is then supported on configuration where the constant spin on all of these components is the same. So we'll have to do a bit of a long-winded route to keep all of the relevant information. So we will first do truncation of the slit strip from above and from below to actually get a finite graph. And it's on this finite graph that we do the honest conditioning of the Ising model to have locally constant spins on these vertical components. Now, I hope that defines the model, and the idea is, of course, then to first take these truncation heights to infinity, and afterwards take the width of the strip to infinity. And this is the width in lattice units. So this width going to infinity should be thought of actually as a scaling limit. So we're in fact approximating a continuum strip of fixed width by lattice of mesh 1 divided by L. 1 divided by the width in lattice units. So, okay, at least the model is hopefully defined. Then what do we mean by correlation functions of boundary fields and their scaling limits? So the idea is that we have this model which provides us now a random configuration of spins on the vertices of this finite graph, the truncated slit strip. So obviously, a boundary correlation function at these three extremities should be some sort of an expected product of three random variables, one located at the top of the strip, another one located on the bottom right of the strip, and a third one located on the bottom left. And what do I mean by random variables located at those places? Well, simply, for instance, the top one, I let the random variable depend in an arbitrary way on the spin configuration restricted to this row. So I fix an arbitrary function from the possible row configurations of pluses and minuses, and in that function, I input the random configuration restricted to the top row. So that should obviously be the most general boundary field that you can have on the top boundary. And for the bottom right and bottom left boundaries, I play exactly the same game. So I fix functions of the spin configurations, and then in that function, I feed in the random configuration that I see. So then one can start taking the limit of the truncation heights going to infinity. And let me just quickly emphasize that we keep these functions fixed. So even if the model changes, as soon as we change the height of the graph, the probabilistic model does change, but what doesn't change is the function that we apply to the configuration on the top row or at these other three extremities. So in this sense, I'm talking about the same correlation function all along.
Could you actually?
Yep.
Yeah, so of course the size of the model is changing. So, and of course the functions depend on like the width, for example. So how can you keep it? How can you keep it constant?
Yeah, that's an excellent question. So far we're keeping the width constant, and the next step will indeed be taking the width. So the first step is to take the height to infinity, and there you can identify the random variables naturally, like by applying the same function. The next step is much more non-trivial. Is how do you identify with different widths?
Yeah. Okay. Yeah. Sorry. I missed that. Yeah. Sorry.
So once the width is fixed, the infinite height limit sort of makes sense. Well, unfortunately, if you do that like that, without any renormalization, you get trivial exponential decorrelation in the random variables. So in order to see something non-trivial, you need to first renormalize by the appropriate factors that actually depend on the exact random variables that you're looking at. So you need to include some renormalization by factors that depend on the chosen functions. And then this is what we call a boundary correlation function in the infinitely high strip. And the non-trivial question is, how do you identify when you start increasing the widths? The moral idea is that, well, even the dimensionality of the space of functions will increase once you increase the width. So you have to form some sort of an inductive system and an inductive limit, basically. And let me try to, so if you know the transfer matrix formalism, you'll probably make the right guess of how to do this identification. I'll try to describe it without an explicit reference to the transfer matrix formalism. So this is clearly the place where some choices need to be made. So here is my description. Let me only try to emphasize some aspects of it. I claim that there is a basis of functions on the spin configurations in the top row, for instance, which is indexed by subsets of positive half integers less than the width. In such a way that, for instance, the appropriate renormalization factor is multiplicative on which elements you include in that subset, in that set of half integers. So the appropriate renormalization is a product of explicit factors for each element that you include there. Right, and you do similar things, of course, for the bottom right and bottom left. So you find bases of functions with these properties. Okay, and this allows us to identify which field in, let's say, width 37 do I identify with which field in width 42. Namely, I will want to fix finite subsets of positive half integers, and then as soon as the widths are large enough, the corresponding boundary fields make sense. All right, and the idea for doing this comes from the fermionic transfer matrix diagonalization of let's say the fermionic way of doing the transfer matrix formalism. So somehow the half integers that you include are certain meant to be certain fermion modes in the lattice Ising model. I hope that was not too confusing. Here clearly some detailed choices are being made. All right. With that, we hopefully understand what are the scaling limits of correlation functions. So two things remain to be described. Fortunately, the local coordinates is a very simple matter. So the continuum slit strip is just the vertical unit width strip placed symmetrically around the imaginary axis where you remove the negative imaginary axis. So that's a simply connected domain, and you can even provide a global coordinate on it by mapping it to the half plane conformally. And that's done by a completely explicit map. Now, the result talked about the double of the slit strip. So indeed, you can put together two copies of the slit strip and obtain a closed Riemann surface. And for instance, if you did that, that produces these pair of pants geometry as the double, or if you described the original slit strip in the half plane coordinate, that just amounts to putting together with the upper half plane a lower half plane to form a sphere. The one thing that needs to be specified is the local coordinates, and they take these very simple forms, and these are the forms in which circles of fixed radius around the origin get mapped to the horizontal sections in this slit strip and its double. So that is the appropriate way to transform radial quantization in these coordinates to the picture that we're supposed to see in the discrete Ising. All right. So then what remains is only the conformal block, the chiral conformal block. The chiral conformal block is associated to any compact Riemann surface and any number of marked points on the surface. So let me just focus on the case of 3 points because that's what we care about. These 3 points on the surface need to be equipped with the choice of local coordinates. And actually for the fermionic case, one even needs to choose some square roots of derivatives of the local coordinates, but let me try to sweep that detail under the rug. So then a conformal block is just a certain trilinear functional on the vertex operator algebra, which satisfies a system of linear equations. The system of linear equations reads like this. The most important thing is that the linear equations are parameterized by global meromorphic 1/2 forms with poles located only at these 3 points. So those objects sort of parameterize the equations, and in these equations, these F1, F2, and F3 is supposed to be there, are the series expansions of this global 1/2 form in the corresponding local coordinate. And the other object that appears here is the psi, and that's just the generating field of the vertex operator algebra. So it had these Clifford generators in its as its coefficients. This is a lower truncated formal series. This is a formal series. Their product makes sense. So this object within the curly braces makes sense, and you can pick the coefficient of z1 to the power -1. That's the formal residue of it. So 3 such formal residues built from the global 1/2 form have to add up to 0. Those are the conformal block equations. For concreteness, one could take a look at what is the chiral 3-point conformal block on the Riemann sphere with the 3 points infinity, 1, and 0. With respect to the most standard choice of local coordinates that you can imagine. It just turns out that this trilinear gadget is well, up to a constant that cannot be determined by the linear homogeneous system of equations, of course. It's equal to what you obtain as a matrix element of the vertex operator map. And the way to see that is basically just writing down global meromorphic 1/2 forms with poles in the right places is easy. You can use this one with appropriate choices of integers a and b. And then the conformal block equations are equivalent to just the Jacobi identity axiom for vertex operator algebras. And this observation even gives you a recursive procedure of determining the conformal block, recursively in adding the fermion generators. So this is with respect to the basis of the vertex operator algebra that we used earlier. Now I realized that I'm actually low on time. But I hope that in some sense, all of the objects appearing in this statement have been explained. And I wanted to make brief comments about the ideas in the proof. I think I will summarize that to just 3 bullet points. So the first one is that one should describe the conformal block in the local coordinates of the slit strip. The idea is to find a recursion for that, and that takes the nicest possible form. So we want to find the nicest possible global 1/2 forms, and for that purpose, we build them from actual holomorphic functions on the slit strip, just appropriately Schwarz reflected to the double. And when the holomorphic functions satisfy something known as Riemann boundary values, and this is exactly the types of boundary values we know how to handle in the discrete with the discrete holomorphic techniques that have been developed starting from the works of Smirnov. All right. So correspondingly for the lattice model, one wants to find a recursion that determines these boundary correlation functions. So that can be done in the transfer matrix formalism by building some discrete analogs of fermionic currents that are appropriate combinations of holomorphic and anti-holomorphic fermion operators there. And they should come with coefficient functions which are taken to be discrete holomorphic functions with Riemann boundary values on the lattice. And the only thing that remains then is to show that the recursion coefficients actually converge. So these recursions become asymptotically the same as you pass to the scaling limit. And this is indeed just obtaining some relatively standard by nowadays standards convergence results for these discrete holomorphic functions. I think I was supposed to end at these 45 minutes. So I wanted only to have a couple of perspectives. So far, this result applies to a very specific setup, but it does capture, in some sense, the full algebraic structure of a conformal field theory. So one could hope for boundary correlation functions in more general domains, not just this slit-strip, or with arbitrary numbers of points. Maybe one natural question is, were we really forced to have these locally monochromatic boundary conditions? Could we have done free and monochromatic boundary conditions? My answer is that I don't currently know how to handle the discrete details with such a combination, but it would be interesting to know. Can we do anything similar for bulk instead of boundary? Do we have any full algebraic structure of a conformal field theory for other critical lattice models? So those would be interesting things to study in the future. But yeah, thanks for the invitation. Thanks for your